Okay, so in this video, what I'll be doing is, I'll be taking up some important numericals on networking, especially numericals dealing with data and signals. Now, before I take up the sums, what I would like you to do is note down these points. So first is, what is bitrate? So as you know, bitrate is the number of bits transmitted per second, and bitrate is measured in BPS. Bitrate is measured in bits per second or in orders higher than bits per second. That means it can be bits per second or its higher magnitudes. That means it can be kilobits per second or megabits per second and so on. Okay, so that's the unit of bit rate. And what about baud rate? Baud rate is the number of signal elements that are transmitted per second. That means, what do you mean by signal element? A signal element is a carrier for your bits. That means you will have some information to transmit. Now that information will, when it will be encoded into a signal, will involve the use of carrier signals. Now those carrier signals, what they'll do is, they'll take those bits and transmit them to the required destination. So you need to know the unit of signal elements, and the unit of signal elements is baud. And what is baud rate? Baud rate is the number of signal elements transmitted per second. And the unit of baud rate or the unit of signal rate is baud. And it's important to know that the baud rate is always lesser than or equal to the bit rate. And the formula, remember the formula, the relation between bit rate and baud rate, this will be very helpful for us. So S denotes the baud rate, S denotes the baud rate, and it is given as N into 1 by R, where N denotes your bit rate. So N denotes your bit rate and S denotes your baud rate. And what does R denote? So remember, R denotes your number of data elements in a signal element. So it is data elements per signal element. That means how many bits. So let me just write this down, per signal element. Here R refers to the number of data elements per signal element. This means that how many bits every signal will be transporting. Okay, let's say you have a carrier signal such that each signal unit is able to transmit 4 units at a time. That means your R will be 4. So R is, like I mentioned, that bits will be carried by signal units, and the number of bits that are transmitted by each signal element or by each signal unit will be the value of R. So here data elements refers to the number of bits. So if you have 4 bits being transmitted or being carried by each signal element, then the value of R will be 4. Okay. And now the question is, what is a carrier signal? So what I would say is, you please note down, I'll dictate what is a carrier signal. You please write it down. In analog transmission, the sending device produces a high frequency signal that acts as a base for the information signal. This base signal is called the carrier signal or carrier frequency. The receiving device is tuned to the frequency of the carrier signal that it expects from the sender. Full stop. Digital information then changes the carrier signal by modifying one or more of its characteristics, which include amplitude, frequency, or phase. This kind of modification is called modulation. I'll repeat the entire thing again. What I would say is, you pause the video from time to time and you note it down. So what is carrier signal? In analog transmission, the sending device produces a high frequency signal that acts as a base for the information signal. This base signal is called the carrier signal or carrier frequency. The receiving device is tuned to the frequency of the carrier signal that it expects from the sender. Full stop. Digital information then changes the carrier signal by modifying one or more of its characteristics, which include amplitude, frequency, or phase. This kind of modification is called shift keying or modulation. So I hope you have understood what a carrier signal is. See, what I said, what I dictated, I'll just sum it up in short. See, a carrier signal is nothing but, it's like this. Let's say you have, okay, what I'll do is I'll just erase the board for a moment. So you please note down whatever I have written on the board. You pause the video and note it down. And let me just give you a brief idea about a carrier signal. So what happens is you have your original signal. Let's say the original signal is in this form. This is your original signal and this is called a baseband signal. This is called a baseband signal. Now what happens is, as you can see, the frequency of this baseband signal or this unmodulated signal. What is a baseband signal? Baseband signal is your analog signal in its original form when it has not been modulated. So this is your baseband signal. Now what you want to do is you want to transmit this baseband signal. Now since this baseband signal does not have that much of intensity, it will not be able to travel a long distance. So what you do is you pass it through a modulator. You pass it through a modulator, and what does this modulator contain? This modulator contains something known as a carrier signal. It contains something known as a carrier signal. This is a pretty sketchy diagram, but I think you can understand the logic. So a modulator will contain a carrier signal of very high frequency. Now this baseband signal will be combined with this carrier signal. Okay, like if you have noted down what I said, I had mentioned in one line that the carrier signal, this is the carrier signal of very high frequency. The carrier signal acts as a base. It acts as a base for your unmodulated signal or for your original signal. So this carrier signal and this baseband signal will be combined to produce a new signal or a modulated signal. This baseband signal and this carrier signal, this is the carrier signal. This is the carrier signal. Both of them will be combined to produce a modulated signal. And this modulated signal will be somewhere in between. Okay. So as you can see, well, this is obviously not an accurate diagram, but the modulated signal will have a frequency which is greater than your baseband signal, and as a result you will be able to transmit your original information across a long distance. Now what will happen at the receiving end? At the receiving end you will have something known as a demodulator. The demodulator, what will it do is it will take this frequency, it will take this wave, or it will take this signal, and it will separate out the original signal from the carrier signal. Okay, remember the modulator as well as the demodulator will use the same carrier signals. They'll use carrier signals with the same frequency. As a result, a demodulator will be able to extract the original baseband signal from the combined signal. So I hope this part is pretty clear to you. Now what I'll do is I'll take up numericals on this topic. Okay, so what I would urge you to do is you first pause the video and copy down the question. So I hope you have copied down the question. Now as you can see, so you can probably read it for yourself, but what I'll do is I'll just sum up the information that has been given to me. So I have been given the baud rate. So I'm solving it now. So my baud rate has been given to me. The baud rate, as you can see, is 40 signals per second. So baud rate is 40 signals per second. Now remember, writing signals per second is same as, like, instead of writing signals per second, even if the question had only baud, it means the same thing, because one baud refers to the number of signals transmitted per second. And what does each signal element consist of? See, I'll repeat once again. One baud is the number of signal or number of signal elements or number of signals transmitted per second. And what does every signal element or every signal consist of? Every signal element consists of bits. So every signal is made up of bits, and you take multiple signals and you get signal elements, right? You take all your signals, and the number of signals or number of signal elements you're able to transmit per second will give you your baud rate. So number of bits you're able to transmit every second constitutes your bit rate, and number of signal elements you're able to transmit per second constitutes your baud rate. So a baud refers to a signal element. Okay, here your baud or baud rate refers to the number of signals transmitted per second. Okay, so I hope this part is clear. So instead of writing signals per second, even if I had written baud, it would have meant the same thing. And I have been given the bit rate. So the bit rate given to me is, as you can see, the bit rate is 1600 BPS, 1600 bits per second. Now I have been asked to find the coding rate. Now what do you mean by coding rate? Here, remember, so what are you trying to code? You're trying to code bits, or you're trying to group bits into signals, right? You're taking multiple bits and you're giving it to every signal element. So coding rate refers to the number of bits you are giving to every signal element. Now in order to find that out, if you remember the formula is S is equal to N into 1 by R, where S refers to your baud rate, N refers to your bit rate, and R refers to this coding rate. See, I'll show you. So what will be R? R is nothing but N divided by S. Now what is N? Now let me solve this here. So what is N? So R is N. What is N? N is your bit rate. Your bit rate is 1600. Is 1600 bits per second. Is 1600 bits per second. And what is your baud rate? It's 40 signals per second. So it is divided by 40 signals per second. Now, if you solve this, what will you get? It's important to understand the unit of R. That means it's important to understand the unit of coding rate. So you will get 1600 bits per second divided by, so this will go up. So you get second divided by 40 signals. Now second and second cancels out and you're left with, so here a 0 and 0 will cancel out. 4 goes into 160 40 times and you're left with a value of 40 bits per signal. So this is your answer. So this is your coding rate. The coding rate is 40 bits per signal. What does this mean? This means that every signal element will be given the responsibility to transport 40 bits. Okay, 40 bits. Every signal element will be given the responsibility to transport 40 bits. This is the meaning of coding rate. Okay, so I hope this part is clear. What I'll do is I'll take up another sum. So you can please pause the video and copy down the question. So I hope you have copied it down. Again, what I'll do is I'll just sum up the information that has been given to me. Now they're talking about ASK, that is amplitude shift keying. So here we are dealing with amplitude shift keying. So keying refers to, shift keying refers to modulation, right? So in amplitude shift keying, or ASK in short. Okay, so we are dealing with an ASK system and we have been given the bit rate. The bit rate that has been given to us is, the bit rate is 2000 BPS, and it has also been mentioned that the transmission mode is half duplex. Remember, for ASK systems, the bit rate, okay, in short I'll write bit rate as N. So from the formula, if you remember the relation between bit rate and baud rate, I had written S is equal to N into 1 by R, where S is your baud rate and N is your bit rate. So here you can see that the bit rate is 2000 bits per second. Just keep in mind that for ASK, for amplitude shift keying, your bit rate is same as your baud rate. Okay, your bit rate is same as your baud rate, and also the bandwidth is same as the baud rate. The bandwidth is same as the baud rate, making the bandwidth same as the bit rate as well. So here we have been asked to find the minimum bandwidth and we have been given the bit rate. Since we have been given the bit rate as 2000 bits per second, what is the baud rate? The baud rate will also be 2000 signals per second. I can write 2000 signals per second, or you can write this as 2000 baud, because that is the unit of signal rate. Okay. And next is, so this is my baud rate coming from this relation, and I have been asked to find the minimum bandwidth. And remember, it's a half duplex system. It's a half duplex system. So bandwidth I know from the property of ASK, I know that the bandwidth is same as the baud rate. My baud rate is 2000. That means my bandwidth will also be 2000. The unit will be hertz. And since it's half duplex, I will leave it at 2000. Had it been full duplex, I would have had to multiply it by 2. Okay. So I hope this is understood. Now I'll take up another question. So let's solve another question here. You can please pause the video and copy down the question. So let me explain this. So I have been given a bandwidth of 5000 hertz. I have been given a bandwidth of 5000 hertz. Okay, it's an ASK signal again, like we saw previously. Just now in question number 2, we saw an ASK system. Again, we have been given another ASK system where the bandwidth has been given to us. Now, interestingly, the bandwidth which has been given to us is 5000 hertz. The bandwidth is 5000 hertz, and they have not mentioned anything about the transmission mode, whether it's half duplex or full duplex. That has not been mentioned, so we can assume it to be half duplex. Okay, so the bandwidth that has been given to us is 5000 hertz, and we have been asked to find the baud rate and bit rate. So previously we saw that the relation between bandwidth, baud rate and bit rate for an ASK system. Remember, for an ASK system, your baud rate and your bit rate are same. Your bandwidth is same as the baud rate. Now, since I have been given the bandwidth of 5000 hertz, I can easily conclude that my baud rate is 5000 as well. I can write 5000 baud, or I can write 5000 signals per second. And I can find the bit rate easily because I know that the bit rate is same as the baud rate. So I'll write 5000 for bit rate as well. And what is the unit? 5000 bits per second. So if you know the property of each of the analog systems, ASK, FSK, PSK, then solving the sums becomes easy. I'll take up another question. Okay, I would urge you to pause the video and copy down the question, as well as the information regarding frequency shift keying. You please copy all this down. So I hope you have copied down everything. Now, what I'll do is, you can probably understand this. Let me try to explain the formulas, let's say, that you need to keep in mind for solving sums on FSK systems. The first thing is FSK stands for frequency shift keying, where you altered the frequency of an analog signal in order to produce a corresponding digital signal, right? So here ASK, FSK and PSK, what are these? These are analog to digital transmission techniques or analog to digital conversion techniques. If you want to convert an analog signal into a digital signal, you either use ASK or FSK or PSK. So an analog signal can be characterized by 3 parameters: amplitude, frequency and phase. If you alter any one of the characteristics, what you can do is you can produce a corresponding digital signal. So if you altered the frequency and take necessary steps, then you can produce a digital signal, and the process of altering the frequency to produce a digital signal is known as frequency shift keying. Okay, so here you can see that the bit rate and the baud rate again are same. Like you saw in amplitude shift keying, here also in frequency shift keying, the bit rate and baud rate are exactly the same. And what about the bandwidth? The bandwidth is given by this formula. So again, since you are talking about transmission, there will be carrier signals. Now, in order to find the bandwidth, what you do is you take the highest carrier frequency, that means the highest frequency value of your carrier signal, and you take the lowest frequency value of your carrier signal. you subtract it, and you add it with the baud rate to get the bandwidth. Okay, so this is the formula. Now, let's just put these formulas into effect by solving this question. So what I'll do is I'll just sum up the information that has been given to me. Firstly, it is an FSK system, that is pretty clear. Also, we have been given the bit rate. The bit rate has been given to be 2000 bits per second. And it has also been mentioned that the transmission is half duplex. That is also understood. And the carriers are separated by 3000 hertz. This is interesting. Your carriers are separated by 3000 hertz. This means that the difference in the carrier frequency is 3000 hertz. That means this value, FC1 minus FC0, this happens to be 3000 hertz. So you have to find the bandwidth. So in order to find the bandwidth, what you do is you use this formula, you apply this formula which I have written. So what is the difference in the carrier frequency? The carriers are separated by 3000 hertz. That means the difference between the highest carrier frequency and the lowest carrier frequency of the carrier signal is 3000 hertz. So I can place 3000 in place of this term. And what is the baud rate? See, the baud rate has not been given to me, but I know from this relation that the bit rate is same as the baud rate. From this relation, I can conclude that the baud rate is same as the bit rate, which is 2000. So my baud rate is 2000 signals per second. Now, if I add these two, what do I get? I get 5000 hertz. Okay, so this is the minimum bandwidth for an FSK signal asked in this question. I'll take up another question. So I would urge you to pause the video and copy down the question. So if you have copied down the question, here you can see what I'll do is again, I'll sum up the information that has been given. I've been given the bandwidth, and the bandwidth is 12,000 hertz. Okay, so let me write down the bandwidth. The bandwidth given to me is 12,000 hertz. But that is not the only information that I've been given. I've also been given that the transmission mode happens to be full duplex. Now, since the transmission mode is full duplex, I need to consider not 12,000 hertz, but 6,000 hertz. Remember, if the transmission is full duplex, then what you need to do is you need to consider the bandwidth for one end only. Since you're considering bandwidth for one end only and the transmission happens to be full duplex, that means this is the bandwidth for the entire transmission. That means transmission from the sender to the receiver as well as back from the receiver to the sender. So since this is the total bandwidth and the transmission mode is full duplex, in order to calculate the bit rate, you need to consider the transmission bandwidth or the medium bandwidth for one end only. And in order to find the medium bandwidth for one end only, you need to take your bandwidth and divide it by 2. So here what I'll do is, in order to get the maximum bit rate for an FSK signal, and since the transmission is full duplex, I will take this number 12,000 and I'll divide it by 2. So I'll take 12,000 hertz and I'll divide it by 2 and I'll get 6,000 hertz. So 6,000 hertz is my bandwidth. And it has also been given that the carriers are separated by 2,000 hertz. That means this term, the difference between the highest and lowest carrier frequency is 2,000 hertz. So this value of FC1 minus FC0, the difference between my carrier frequencies is given as 2000 hertz, and I have been asked to find the bit rate. Now, there is no relation, as you can see from the board, there is as such no relation between the carrier frequency, the bandwidth and the baud rate. But if I am able to find the baud rate from these two terms, then I'll be able to find the bit rate. Why? Because for an FSK signal, the bit rate is same as the baud rate. So what I'll do is I'll first find the baud rate using this formula. So I'll not write down the formula here. In your examination, you need to mention the formula, mind you. Okay. So since I've already written the formula here, I'm not writing it here again. I'll directly find the baud rate. So I'll just place the terms here. So what is my bandwidth? My bandwidth is 6,000 hertz. Why did I consider 6,000 and not 12,000? The reason is the transmission mode is full duplex, and in order to find the maximum bit rate, I need to consider the bandwidth for one end only. For both ends, the bandwidth is 12,000. So the bandwidth here is 6,000. So I place 6,000 here in this formula, I place 6000 because bandwidth is 6000. Now this difference has been given to be 2000. And what is the baud rate? Baud rate is given by S. So now what will be the value of S? The value of S will be 6000 minus 2000. That is 4000 baud. And what do I know? From this relation, I know that the bit rate and baud rate are same. So I can say that my bit rate happens to be 4000 as well. And what is the unit? The unit is bits per second. So this is my final answer. Okay, so I hope this is understood. Now I'll take up another question. Okay, now you please copy down this question and I'll proceed with the solution. So I hope you have copied it down. Now we are dealing with another system of analog to digital conversion, not transmission, conversion. This is called PSK. PSK stands for phase shift keying. As you can see, I have written a few formulas. So you may be given an N PSK system. Like here in this question, you have been given a 4 PSK system. Now, how do you find the bit rate? You take the log of the N value which has been given to you and you multiply it with the baud rate. Okay, that will give you the bit rate, and remember the bandwidth is same as the baud rate. So let us solve this. So okay, I'll take another pen here. Yeah, so let's see how this turns out. So here we have been given the bit rate. As you can see, the bit rate has been given to us. The bit rate has been given to us as 2000. So the bit rate is 2000 bits per second, and it has also been mentioned that it's a half duplex system. Now along with this, we have been given a 4 PSK system. That means the value of N is 4. The value of N is 4. And now we have been asked to find the bandwidth. Now we know that there is no relationship. From this formula, you can understand that there is no relationship as such between bit rate and bandwidth. But there is a relationship between bandwidth and baud rate. And if I am able to find the baud rate using this formula, then I'll easily be able to find the bandwidth. So let me first find the baud rate. So I'll apply this formula. So baud rate will be the bit rate, that is 2000. Okay, let's change my pen here. So my bit rate, which is 2000. So I'll take the bit rate of 2000 and I'll divide it by log 4 base 2. Now this, as you know, so if I simplify this, I get 2000 divided by, so 4 can be written as 2 to the power of 2 base 2. Now this 2, which is at the top, which is at the power, I can bring it here at the beginning. So log 2 base 2 is 1. So at the denominator I have only 2. So if I divide 2000 by 2, I get 1000. So my baud rate comes out to be 1000 baud. Now from this relation, you can understand that the bandwidth is same as the baud rate. So I can say that my bandwidth is also 1000, but the unit is hertz. Okay, so this is how you solve such questions. What I'll do is I'll take up another question. Okay, now again, you please pause the video and copy down the question. So I hope you have copied down the question. Now let's solve this. Again, it's a PSK system and we have been given a bandwidth of 5000 hertz. Okay, so the bandwidth is 5000 hertz and it's an 8 PSK signal. So the value of N is 8 and we have been asked to find the baud rate and the bit rate. So if you remember, the relationship between bandwidth and baud rate for a PSK system is that the bandwidth and baud rate are same. Here we have been given the bandwidth. So from the bandwidth, we can conclude that the baud rate is also 5000. The baud rate is also 5000, but the unit is baud. The unit is baud. And now we know that what is the relationship between bit rate and baud rate? The relationship is defined as bit rate is equal to log n base 2 into the baud rate into the baud rate. Now, what is the value of n? The value of n is 8 base 2. And what is my baud rate? My baud rate is 5000. Now, if I simplify this, I get 2 to the power of 3 base 2 into 5000. And now I can take this 3 and I can bring it at the beginning by the property of logarithms. And log 2 base 2 is 1. So I get 3 into 1 into 5000. So this comes out to be 15,000 bits per second. Okay, so this is how you would solve such a question. I'll take up another question. Okay, again, pause the video and copy down the question. So I hope you have copied down the question. Now we have been asked to calculate the bit rate for 1000 baud 16 QAM signal. What is QAM? QAM, if you remember, QAM stands for quadrature amplitude modulation. So it stands for quadrature amplitude modulation, and it is formed by combining ASK and PSK. Okay, so you combine the techniques of ASK and PSK to get QAM. See, the logic still remains the same. You have been asked to calculate the bit rate, and we know that the bit rate is given as, okay, yeah, I can write it here. So it is given as log n base 2 into the baud rate. Now, here, what is the value of n? The value of n is 16, because it's been given 16 QAM. So the value of n is 16. So I'll write log 16 base 2 into the baud rate. The baud rate is 1000. So now, again, log 16 base 2 can be evaluated as 2 to the power of 4 base 2 into 1000. Now this 4 can be brought here. So log 2 base 2 is 1. So that's 4 into 1 into 1000, which comes out to be 4000 bits per second. It comes out to be 4000 bits per second. So I hope you have understood this question. I'll move on to another one. Please copy this question. Okay, now let's solve this. So we have been asked to compute the baud rate, and we have been given the bit rate. Now the bit rate, in short, given as n, is 72,000. The bit rate is 72,000 BPS. And what is the value of n? The value of n is 64. This value of small n, mind you. The capital N denotes bit rate. This capital N symbol denotes the bit rate, and small n denotes the order of the encoding technique. So the technique that you're using here is QAM, and its order is 64. So the value of small n is 64. Now, in order to find, what is the relationship between bit rate and baud rate? If you remember, bit rate is given as log n base 2 into my baud rate, which is written as n, or which is denoted by S, which is denoted by capital S in short. So here my small n is 64, the order is 64, and my baud rate is unknown to me, but the bit rate has been given. The bit rate is 72,000. I'm simply putting the values. I'm putting 72,000 for my bit rate and 64 for my order, which is small n. Now I can find S. Simply by dividing 72,000 by, now 64 can be written as 2 to the power of 6 base 2. Now this 6 can be brought in front by the property of logarithm, and now I have log 2 base 2. So log 2 base 2 is 1. So this will come out to be 72,000 divided by log 2 base 2 is 1 divided by 6. So this will give me 12,000. So 12,000 is my answer. 12,000 baud is the answer for this question. So the baud rate in this case is 12,000 baud. I'll take up another question. Okay, so let's see this. Okay, we have been asked to fill up this table. So the bit rate column is empty, as you can see, and you have been given various modulation techniques. The baud rate has been given. The baud rate is n in all cases, and you have been asked to fill up the bit rate. So let's see how we do this. Now, if you remember, for ASK and FSK, the bit rate and the baud rate are exactly the same. The bit rate is equal to the baud rate. In amplitude shift keying and in frequency shift keying, the bit rate and baud rate happen to be the same. Now here the baud rate is n, so the bit rate for ASK will also be n. For FSK it will also be n. Now what about 2 PSK? The order in this case is 2. If you remember, the formula was my bit rate is given as log of the order with base 2 multiplied by the baud rate. This was the formula. Now here S stands for your baud rate and your N stands for your bit rate. The capital N stands for bit rate and small n denotes the order of modulation. Small n denotes the order of modulation. So now what we do is what is the value of n here? The value of small n is 2, right? So if you place 2 here, you get log 2 base 2. What is log 2 base 2? Log 2 base 2 is 1. And the baud rate has been given to be capital N. So what is 1 into n? N itself. That means the bit rate in case of 2 PSK is also n. Similarly, what about 4 PSK and 4 QAM? Now here the order is 4 in both cases. So in place of small n, you will substitute 4. And what is log 4 base 2? Log 4 base 2 happens to be 2. And the baud rate that has been given to you is n. So what is 2 into n? N itself. Now I'll use a different term here. I'll use b to denote bit rate only in this case, because the baud rate has been given to be n and you might get confused. That's why I'll use b to denote my bit rate. B here denotes my bit rate. Okay, and n denotes my baud rate. So as I can see, the bit rate will now be given as 2 into n. So that is 2n, and it will be the same for 4 QAM as well. So in both cases, it will be 2n. So I'm not writing it separately. In this case, the order is, in both cases, for 8 PSK as well as for 8 QAM, the order is 8. In both cases, the order is 8. So you will substitute in place of 4, 8, and this term will come out to be, what is log 8 base 2? Log 8 base 2 is 3. Log 8 base 2 is 3. So what is 3 into n? 3 into n is 3n. And what about 16 QAM? 16 QAM means your n, your small n will be 16. So what is 16? 16 is 2 to the power of 4. And here you will get 4. So what is 4 into n? You will get 4n. Similarly here, the order is 32. So in place of small n, you will substitute 32. So what is log 32 base 2? Log 32 base 2 is, 32 is 2 to the power of 5. So you can bring the 5 at the beginning. So log 2 base 2 is 1. So here the value will come out to be 5. So what is 5 into n? 5n. Similarly, 64 is, you place 64 here in place of small n, and you get this value as 6. So the answer will be 6 into n, 6n. Similarly, you place 256 here. So in place of 64, the order is now 256. So what is 256? 2 to the power of 8. So here you get the value as 8. So the answer is 8n. The answer is 8n. So I hope this is understood now, the relationship between the order of modulation, bit rate and baud rate. I'll take up another sum. Okay, please copy down this question. This numerical is based on multiplexing. What I'll assume is you already have sufficient background knowledge on the topic of multiplexing in computer networks. If you have any doubts, what I would say is you go back to a video which I recorded earlier, which you can probably find the link to it in the top right corner of your screen. So you can go to that link, you can watch that video and come back and see the solution to this problem. Okay, so I hope you have copied down the question. Now, what I'll do is again, I'll sum things up. So I have been given, okay, before I proceed to this, remember, a link is same as a transmission medium. The word transmission medium and link are used simultaneously. These two words are used simultaneously. And remember, for multiplexing, what do? We take a link and we divide it into n number of channels so that its bandwidth can be made use of effectively. This is the objective of multiplexing. And since I made this point, I need to extend it a bit further. See, if you're going to divide a link into multiple channels, and what you need to do is you need to ensure that these channels do not overlap, because each of these channels will be transmitting different kinds of signals, and there is a high chance of these signals overlapping. So what you do is you insert some guard bands. Now, what are these guard bands? These guard bands are extra orders of bandwidth which are used to separate the channels so that there is no interference among the signals transmitted by each of the channels, and there is no distortion or there is no harm brought to the ultimate signal that is going to reach the destination. Okay, so for that we use guard bands. Now here what you have is you have 6 channels. So a link has been divided into 6 channels. I am denoting every channel by this box. Okay, so I have how many boxes? I have 6 boxes, right? Each box denoting a channel. So 1, 2, 3, 4, 5 and 6. So I have 6 boxes, 6 channels, and now there is a guard band, right? There is a guard band shown by this arrow. So there is a guard band. There has to be a guard band between every pair of adjacent channels. What are adjacent channels? Channels which are side by side. So I need a guard band between these 2 channels, between these 2, between these 2, between these 2 and between these 2. So I need to insert guard bands between adjacent channels, channels which are placed side by side, one after the other. And now, as you can see, for 1, 2, 3, 4, 5, 6 channels, each having a bandwidth of 90, each having a bandwidth of 90 kilohertz, how many guard bands do I need? Each guard band, as you can see here, which is of, I think, 5 kilohertz, right? Yeah, the guard band frequency is 5 kilohertz. So this is also 5 kilohertz. This is 5 kilohertz. So is this. And so is this guard band. So how many channels do I have? I have 1, 2, 3, 4, 5, 6 channels. And how many guard bands do I have? I have 1, 2, 3, 4, 5. From this, you can note down an important relation between the number of channels and the number of guard bands. If you have a link divided into n number of channels, to ensure that there is no interference, you need n-1 guard bands. Okay, so I have 6 channels here. I required 5 guard bands. Now, what you need to do is you simply need to now sum up the frequencies. So I have 6 channels. So what is the total frequency? I have been asked to find the minimum bandwidth of the link. That means the sum of all these frequencies, right? The sum of all these bandwidths will give me that value, which should be the minimum value of my entire link, so that such a configuration is made possible. See, in order to make this configuration possible, I need a link which is of a capacity to accommodate the final value. See, this is actually enclosed inside one large transmission medium. So this is this outer box that you see, this is the link. This link has been divided into so many channels. Now, in order to accommodate this facility, what should be the bandwidth of the link? The bandwidth of the link should be a minimum of the sum of these values, because if the bandwidth is anything less than this, you will have to compromise on one of these things, and in that case your transmission will be hampered. So the bandwidth of the entire link should be at least the same as the value of the sum of these bandwidths. So what will be the sum? The sum will be of 6 channels. So each channel has a bandwidth of 90. So that comes out to be 19 to 6 kilohertz. 6 channels. Each channel has a bandwidth of 90. So total bandwidth of all the channels is 90 into 6. And how many guard bands are there? 1, 2, 3, 4, 5. 5 guard bands. And each guard band has a bandwidth of 5 kilohertz. So that will be 5 into 5 kilohertz. So what will be the total of this value? This will be 540 and this will be 25. So it comes out to be 565 kilohertz. That means the capacity of your link, which is accommodating so many channels as well as the guard bands, should be at least 565 kilohertz. See, if it's more than that, it's fine. But it should be at least 565. Anything less than 565 would mean compromising on your transmission process. So I hope this is understood. Now I'll take up another question. So please copy down this question. You have been asked to find the Hamming distance between this bit sequence and this bit sequence. So how do you find the Hamming distance? I'll show you. So this is your first bit sequence and this is your second bit sequence. Now you check the corresponding bit positions. So I'll check the least significant bit position. I can see that the bits are differing. So I'll increase my Hamming distance count by 1. Now I'll check this position. They are having the same bit values. So I'll not increase the count. Again, the bit positions here, in this case, the third bit position from the right are differing in values. So I'll increase my Hamming distance count by 1. I'll look at this position again. They are differing. So I'll increase my Hamming distance count by 1. These two bits are same. In the MSB, I can see that there is a 1 and there is a 1 here as well. So I'll not increase the Hamming distance count. So my Hamming distance comes out to be 3. Okay, so this was pretty straightforward. Now I'll move on to another sum on Hamming codes. Okay, let's look at this question now. You have been given a bit sequence, as you can see here, 1011, and you have been asked to construct the even parity Hamming code. Okay, now let's see how you can construct the Hamming code sequence. See, firstly, what you need to find is, you need to find the number of redundant bits. You need to find the number of redundant bits. You need to find the number of redundant bits to add to your original bit sequence. Now, what are these redundant bits? These redundant bits are nothing but your parity bits. These redundant bits are nothing but your parity bits. So what you do is, you have to decide upon which parity sequence you're trying to work with. So here it has been given that you have to use even parity. So you will have to add your parity bits in such a way so that even parity is followed. Now the question is, how many redundant bits do you add? That question is answered through this relation. Remember, there is this relation, 2 to the power of r is greater than or equal to r plus m plus 1. Here r denotes the number of redundant bits or parity bits for that matter. So r denotes the number of parity bits and m denotes the number of message bits. The number of message bits. Now using this relation, you will be able to find the number of parity bits that you require. We know the value of m. What is the value of m? The value of m is 1, 2, 3, 4. Number of bits present in the original sequence. So what is the original sequence? 1011. So how many bits are there in 1011? 4. So here the value of m will be 4. So I have 2 to the power of r on my left hand side and I have r plus 4 plus 1 on my right hand side. That means on my right hand side I can write this as r plus 5. Now I have to choose the value of r in such a way that the relation greater than or equal to is satisfied. Now how do you choose the value of r? You choose the value of r through trial and error. So you start with the smallest possible value of r. The smallest possible value that r can take is 1. You add 1 redundant bit. So if you add 1 redundant bit, what do you get? You get 2 to the power of 1 here, which is nothing but 2. And here you get 1 plus 5. You get 1 plus 5. So this is for r is equal to 1. So in this case, you get 2 on the left hand side and you get 1 plus 5, which is 6 on the right hand side. But 2 is not greater than or equal to 6. So we will reject this. Next, we will try with r is equal to 2. Now with r is equal to 2, you get, on the left hand side, you get 2 to the power of 2, which is 4. And on the right hand side, you get 2 plus 5, right? You get 2 plus 5, which is 7. Now we know that 4 is not greater than or equal to 7. So we reject r equal to 2. Next, we place r is equal to 3. So if I place r is equal to 3, on the left hand side, I get 2 to the power of 3, which is nothing but 8. And on the right hand side, I get 3 plus 5, which also happens to be 8. Now you see this relationship is satisfied because 8 is although not greater than 8, but it is equal to 8. See, the relation is either greater than or equal to. So for a value of r is equal to 3, I am able to satisfy this relation. So how many redundant bits do I have to add? I have to add 3 redundant bits. Okay. So one thing is for sure, that we have to add 3 redundant bits. Now, our work doesn't stop here. We have been asked to construct the even parity Hamming code. Now this even parity Hamming code refers to the bit sequence which you obtain after appending the 3 parity bits with your original bit sequence. Now let's see how we can come up with this original bit sequence and parity bits taken together to form the Hamming code. Okay, so let's see this. So I'm erasing this. I hope you have paused the video and copied everything down. Now what you do is you simply write the bit positions. You simply write the bit positions in this manner. So you write D1. So these are your bit positions, okay? So this is D1, this is D2, D3, D4, D5, D6 and D7. Why have I written 7 bit positions? Because I have 4 bits in my original sequence and just now I found out that I need to add 3 parity bits. Okay. So here I have 7 bits. Now what will I do? How do I find the position of my parity bits? See, I need to add how many parity bits? I need to add 3 parity bits. Fine. So I need to add, let's say, parity bit 1, parity bit 2 and parity bit 3. Now how do I find the parity bit values as well as their positions? Remember, parity bits will always be placed in positions of powers of 2. That means I'll place my parity bits only in those positions which can be expressed as a power of 2. Can I express 1? Can I express position 1 as a power of 2? Yes, I can. How? I can write 1 as 2 to the power of 0. So my first parity bit, P1, will go here. So my P1 will go here. Similarly, what about D2? Can I express 2, my position 2, right? Can I express position 2 as a power of 2? Yes, I can. I can write 2 to the power of 1. Can I express 3 as a power of 2? I cannot. Can I express 4 as a power of 2? Yes, I can. I can write 2 to the power of 2. Can I express 5 as a power of 2? I cannot. Can I express 6? I cannot. Can I express 7? I cannot. So these will be the positions of my parity bits. So this is the position of the first parity bit, this is the position of the second parity bit, and this is the position of the third parity bit. And what about the remaining positions? The remaining positions are occupied by my original bit sequence. My original bit sequence is 1, 0, 1, 1. So what is the most significant bit? The most significant bit is 1. This leftmost 1 is the most significant bit. So this will be placed at D7. Which is the bit after the most significant bit? Which is the second most significant bit? 0. So 0 will be placed here. Which is the third most significant bit? 1. So 1 will be placed here. And which is the least significant bit? 1. So it will be placed here. Now after determining the positions of my parity bits, I need to come up with values, right? I need to know what is the value of P1, what is the value of P2 and what is the value of P3 in order to be able to construct the Hamming code. This entire 7-bit sequence will be my Hamming code. So I need to find the values of P1, P2 and P3. Now remember, what is P1? P1 will, or let's put it this way, the value of P1 will be such that it is an even parity value, as well as it is dependent on those bit positions which have a 0 in the LSB. I'll show you how. Let's say, let me draw a table for you. So let's say I have a 4-bit sequence. So what is my 4-bit sequence? Okay, let's stick to 3 bits. So I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so there are 8 sequences. Now, we will not consider the 0th sequence. We'll start from 1. Now, let's say this is my P1, this is my P2, and this is my P3. So these are my 3 parity bits. So which bit positions will I look at in order to find the value of P1? I repeat, which bit positions will I look at in order to find the value of P1? I will look at those positions which have a 1 in the least significant bit. So if you can see here, there is a 1 here in the least significant bit. There is a 1 here, there is a 1 here, and there is a 1 here. What is this? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. That means the first parity bit, P1, depends on, or let's put it this way, the P1 parity bit decides the value based on the bit positions 1, 3, 5, and 7. So in order to find the value of P1, I have to look at position 1, that means this position 3, position 5, and position 7. So I can see that position 1, I don't know what is position 1, but I know the value of position 3. The value of position 3 is 1. What is the value of position 5? The value of position 5 is also 1. And what is the value of position 7? It is 1. Now I have to place P1. With either 0 or 1, obviously, because I'm dealing with bits. So it can be either a 0 or a 1. Now the question is, what do I put here? Do I put a 0 or do I put a 1? I have to ensure that even parity is maintained. See, it has been clearly mentioned that you have to maintain even parity. So what is even parity? Even parity means you have to ensure that there are even number of ones. How many ones are here? 3 ones are here. So what should I place in this position so that there are even number of ones? See, if I place 0 here, if I place 0 in this position, what will I get? I'll get odd number of ones because there are 3 ones. But if I place 1 here, I'm getting even number of ones. That means I should place, in place of P1, I should place the bit 1. Okay, now let's try to find the value of P2. Similarly, we'll look at this table. So in this table, we can see that P2 depends on position 2, position 3, position 6, and position 7. So what is position 2? See, position 2 is the position of P2 itself. I don't know. I have to determine the value. But position 3 is known to me, that is 1. Position 6 is known to me, that is 0. And position 7 is also known to me, that is 1. Now, what should I place here so that even after placing a value here, what should I put here so that even after placing a value here, even number of ones are maintained? See, if I place a 0 here, then there are even number of ones. But if I place a 1, then there are odd number of ones. So here I should place 0. That means the value of P2 should be 0. The value of P2 should be 0. Okay, now let's determine the value of P3. Now again, look at this table. Which positions are 1? Last 4 positions, that means positions 4, 5, 6, and 7. Now position 4 happens to be the position of P3 itself. I don't know its value. What about position 5? Position 5 is 1, position 6 is 0, and position 7 is 1. Now what should I place here so that there are even number of ones? I should place a 0. See, after placing a 0, how many ones are here? 2 ones are here. So here I should place a 0. So I should place a 0. So what is the final Hamming code? The final Hamming code is this 7-bit sequence. So the 7-bit sequence is, I'll write it here, 1 0 1 0 1 0 1 0 1. Right? 1 0 1 0 1 0 1. Yeah. So 1 0 1 0 1 0 1. So this is the Hamming code that you have to transmit so that there is a possibility for both error detection as well as error correction. Okay, now I'll take one more example. Okay, now we have moved to the final question in this video. So what I would say is, you please pause the video and copy it down so that we can proceed further. Since you have copied down the question, I have just written the bit word. Okay, this is the bit word which needs to be transmitted to the receiver. Now, while transmission, any one of the bits got corrupted, and we have been asked to use Hamming code to find the position of the bit which got corrupted, and then obviously using Hamming code automatically correct it. Okay, so the first thing that we need to do is we need to find the number of redundant bits to add. Now see, it has not been mentioned the type of parity I have to use, so I'll assume that I'm using even parity. Hamming code by default as such uses even parity, so here also I'll assume that even parity is being used. Now step number 1 is to find the number of parity bits I need. So what was the relation? The relation between parity bits and message bits was 2 to the power of r is greater than or equal to m plus r plus 1. Now here m is the number of bits in my original sequence. So how many bits are there? 1, 2, 3, 4, 5, 6, 7. So the value of m is 7 plus r plus 1. So that means the right hand side has a value of 8. Right hand side has a value of 8. So it's 8 plus r, and the left hand side is 2 to the power of r. Now again, I'll start with trial and error. So first I'll place r is equal to, now it's quite evident that if you place r is equal to 1, it will never be satisfied. If I place r is equal to 2, will it be satisfied? No. If I place r is equal to 3, then also it will not be satisfied. But if I place r is equal to 4, now see, from experience I can calculate this fast. You can also do the same with some practice. So if I place r is equal to 4, then what do I get? Let's just observe. So I get 2 to the power of 4 on the left hand side, which is nothing but 16. And here I get 8 plus 4, which is 12. See, for r is equal to 3, what would I have got? For r equal to 3, I got 8 on the left hand side and 11 on the right hand side. So obviously this is not going to work. But for r is equal to 4, I am able to satisfy the relation. That means I need 4 even parity bits or 4 redundant bits. Okay. Now, the first thing that we do is we encode our original bit sequence. Into the Hamming code. How? Using these redundant bits. How many redundant bits? 4 redundant bits. Okay. There are 4 redundant bits. Now, let me write the bit position. So if I have 1, 2, 3, 4, 7 bits in my original message sequence, and if I have 4 redundant bits, I get a total of 11 bits. So let me just write them down. I'll write here. So D1, D2, D3, D4, D5, D6, D7, D8, D9, D10 and D11. Okay, so this is my bit sequence, right? This is my Hamming code, the 11-bit Hamming code that I want to find out. Now, what about the parity bits? Now, how many parity bits do I have? I have 4 parity bits, right? So I have parity bits 1, parity bits 2, 3 and 4. Now, where do these parity bits go? They'll always go in positions which can be expressed as powers of 2. This is position 1, which can be expressed as a power of 2, 2 to the power of 2, 2 to the power of 0, sorry. So here will be my parity bit 1. This can be expressed as 2 to the power of 1. So this will be parity bit 2. This is 2 to the power of 2. Position 4 can be expressed as 2 to the power of 4. So this is my parity bit 3. Similarly, position 8 can be expressed as 2 to the power of 3. So this is my parity bit 4. Okay, and the remaining positions are occupied by my message bits, which I currently know. So these are my message bits. Which is the most significant bit? The most significant bit is the leftmost one. So I'll place it at D11. Then there is 0. So I'll place them from left to right. So I have 0 here. Then there is another 0. So that's 1 triple 0, 1 1 0. Okay. So this is my message bits written. Now I need to find the values of P1, P2, P3, P4 like I showed you in the previous numerical. So how do I find the positions? Now in order to find the positions, I'll take help of the table, right? Now the earlier table, since there were 3 parity bits to find, here I have to find 4 parity bits. So I'll construct a larger table, the table for a 4-bit sequence. So I'll start with a value of 1. So I'll start with 0, 0, 0, 1, then 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, and finally 1, 0, 1, 1. As you can see, I've stopped at 1, 0, 1, 1. Why? Because I have positions from 1 to 11. So this is for position 1 and this is for position 11. And this is for parity bit 1, parity bit 2, parity bit 3 and parity bit 4. Okay. Now let's try to find the positions which are dependent on P1. Which are the positions? So these are my decimal equivalent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now see, P1, or let's say the positions which depend on P1 are these 1. Wherever you find a 1, those are the positions which are dependent on P1. So 1, 3, 5, 7, 9 and 11. So positions 1, 3, 5, 7, 9 and 11 are dependent on P1. Let's try to find the value of P1. So I don't know the value of P1, but I know what is at position 3. What is at position 3? 0. I know what is at position 5. There is 1. At position 7, there is a 0. At position 9, there is a 0. And finally, at position 11, as you can see, there is a 1. Now, what value should I place here so that there are even number of 1s? I should place a 0. So P1 here will get a value of 0. So P1 gets a value of 0. Next, it's my turn to find the value of P2. Now, again, I'll look at the 1s. So position 2, position 3, position 6, position 7, position 10 and position 11. These positions are dependent on P2. So let me just write these values. Now, see, P2 is dependent on its own position, of course, but that is what I'm trying to find, so I don't know its value. It is dependent on position 3, position 6 and position 7. So what is position 3 having? Position 3 has 0, position 6 has 1, position 7 has 0. So positions 3, 6, 7, as you can see here, there is position 2, there is position 3, and then there is position 6, and then there is position 7. These positions have 1, as you can see. And then you have a 1 at position 10, and then a 1 at position 11 for P2. So what is that position? So I have 2, 3, 6, 7, and then there is 10 and 11. What is that 10? 0. And what is that 11? 1. So there is 0 and there is a 1. Now what should I place here so that there are even number of 1s? I should place a 0 so that there are even number of 1s. See, after placing 0 here, I have even number of 1s. So here P2 will get a value of 0. P2 will get a value of 0. Okay. Now it's time to find the value of P3. Now again, I'm looking at P3. So the column of P3, where do you have 1s? You have 1 at position 4, position 5, position 6, position 7. That's it. So you have 1s at positions 4, 5, 6 and 7. So what is at position 4? At position 4 you have P3 itself. Its value I don't know. At position 5 you have 1. At position 6 you have 1. And at position 7 you have 0. So what should be placed here? So that there are even number of 1s, I should place a 0. So position P3 or parity bit P3 rather gets a value of 0. Now I'll find the value for P4. See, P4 depends on 8, 9, 10 and 11. So 8, so what is 8? 8 is P4 itself. I don't know its value. It depends on, like, positions 9, 10 and 11 are dependent on the position 8, because at position 8 you have P4. And 9, 10, 11 contains 0, 0, 1. As you can see, 9, 10, 11. So that's 0 for 9, 0 for 10 and 1 for 11. So what should I place here so that there are even number of 1s? I should place a 1 here so that there are even number of 1s. So P4 gets a value of 1. So after so much of hard work, I hope you have copied everything down. So I'm erasing this part. So after so much of hard work, we are able to find the Hamming code. Now this Hamming code will be taken and given to the receiver. Now in the question, they have said that we have to assume that any bit, any one bit has been corrupted. Remember, Hamming code is used for detecting and correcting single bit errors. Now, as you can see that this Hamming code sequence comes out to be, I'll just write the entire thing. So it comes out to be 1 0 0 1 0 1 1 0 0 0 0. Let me just check. First check the number of bits. 1 2 3 4 5 6 7 8 9 10 11. Yes, there are 11 bits. And have I written them correctly? 1 0 0 1 0 1 1 0 0 0 0. Yes. So this is the entire thing that will be taken and given to the receiver. Now the question is telling us that we have to assume that at least one bit, not at least one bit, exactly one bit is corrupted. So you can take any bit, okay? So I'll just take one of the zeros. I'll assume that this bit has been corrupted. So it changes. Let's say this bit changes from 0 to 1. Now using Hamming code, we have to detect this error. So how will it be detected? Let's see what goes on at the receiving end. Okay. So we know that we have 4 parity bits. So parity bit P1 depends on positions 1, 3, 5, 7 and 9. Similarly, parity bit P2 depends on positions. What are the positions that P2 depends on? P2 depends on 2, 3, 6, 7, 2, 3, 6, 7, and then it also depends on 10. Okay, let me just pause the video for a moment. I think it's better if I consult the table and then write the values. Then it will be a lot faster. Otherwise, I'll have to construct the table again. So see, I have constructed the table quickly. So this is the table. What you do is you don't need to mug up. See, why did I have to construct the table? Because I don't remember the position values. I don't need to remember the position values. I'll simply remember this table and I'll see where there are ones. I can see that for P1, see, this is my first parity bit. This is for the second parity, third parity and fourth parity. In order to find the positions which are dependent on the first parity, I'll simply check this column where there are ones. So there are ones at 1, 3, 5, 7, 9, 11. So these are the positions on which P1 depends. Similarly, P2 depends on, as you can see, P2 depends on 2, 3, 6, 7. So 2, 3, 6, 7. You skip 8, 9 and then you write 10, 11. That's why, since I didn't remember the values, I had to construct the table once again. And I would suggest that you simply remember this table. And this table is similar to your truth table, right? Truth table for a 4-bit or for 4 variables for that matter. This is the truth table for 4 variables. So you just keep in mind this truth table and it will be enough. You don't need to mug up these positions. You simply write down this table and find the positions for yourself. So what is P3? Now P3 depends on 0, 1, 2, 3, 4, 5, 6. So it depends on 3, 4, 5 and 6. And what does P4 depend on? See, P4 depends on, so there are these last 4 bits. So it's 8. So it's 8, 9, 10, 11. So it depends on 8, 9, 10 and 11. So it depends on 8, 9, 10 and 11. Now what do you have to do? Now you have to find the error codes. You have to find the error codes. So how do you find the error codes? The error codes are found simply in this way. So for P1, what you do is you look at these position values. So what are there at 1, 3, 5, 7, 9 and 11? Let's see. Okay. So for P1, I can see that at position 1. At position 1, so I can just erase this, or yeah, I think what I do is, so here is D1, D2, D3. At D3, let me make the change. At D3, it's 1. Now there is no need to differentiate between parity and message bits. So I'll just erase these boxes. I'll simply box the bit which has undergone a change. This is the bit that has undergone a change. I'll simply unbox this. Okay. Yeah, so this is the, so I can erase this, right? Let me just erase this. Yeah, now look. Now P1 is, or let's say these positions are depending on P1. What are these positions? 1, 3, 5, 7, 9 and 11. So what is at 1? At 1 you have 0. At 3 you have 1. At 5 you have 1. at 7 you have 0, at 9 you have 0, and at 11 you have 1, right? This is what you have. Now what you do is you take XOR of these bits. You take their XOR. Now if I take their XOR, what do I get? 0 XOR 1 is 1. Now in order to answer this, there is a shortcut. What is the shortcut? XOR will produce a 1 if there are odd number of 1s, and XOR will produce a 0 if there are even number of 1s. How many 1s are here? 1, 2, 3. There are 3 1s, so XOR will produce a 1. And this is the value for your error bit. This is the value for your error bit C1. Okay, this is the value of your error bit C1. Now similarly we can find the value of error bit C2. So how do you find the error bit? What is that? Position 2. At position 2 you have a 0. At position 3 you have a 1. At position 6 you have a 1. At position 7 you have a 0. At position 10 you have a 0. And at position 11 you have a 1. See? So that's 0. So how many 1s are there? 1, 2, 3. There are 3 1s. So you will get a 1. So this is the value. So this was the value for error position 1. This is the value for error position 2. Now let's find the value of error position 3. So that's 3, 4, 5, 6. So what is the value of 3? The value of 3 is 1. What is the value of 4? The value of 4 is 0. What is the value of 5? The value of 5 is 1. So I'll be taking the XOR. And what is the value of 6? The value of 6 is 1. So how many 1s are here? 1, 2, 3. There are 3 1s. So I'll simply take the XOR to get 1. So this is the value of C3, right? This is the value of C3, I guess. Yeah, it's 3, 4, 5, 6. So that's 3, 4. Yeah. 0, 1, 2, 3. In fact, I think I made a slight mistake here. It's dependent on, if you see, parity bit P3 depends on, this is 4, right? 4, 5, 6, 7. Yeah, so that's one mistake on my part. I'm really sorry. You please make the change, okay? Really sorry for that mistake. So P3, as you can see, this is the column for P3. Which are the positions which have 1? This has 1, this is 1, this is 1, and this is a 1. So that's 4, 5, 6, and 7. So it depends on 4, 5, 6, and 7. So what is at position 4? At position 4, there is a 0. At position 5, there is a 1. At position 6, there is a 1. And at position 7, there is a 0. So what is the value that you get? How many 1s are here? There are 2 1s. So you get 0. When there are even number of 1s, you get 0. So this is the value of C3. And finally, for P4, it depends on 8, 9, 10, and 11. So 8 has a value of 1. 9 has a value of 0. 10 has a value of 0. And 11 has a value of 1. So this will give you, again, how many 1s are there? Even number of 1s. So the result is 0. And this is the value of C4. So ultimately, what is your error code? The error positions, or let's say, yeah, error position would be a better term. So C4, C3, C2, C1, this comes out to be how much? This comes out to be 0, 0, 1, 1. Once you get this value, you can decide the bit position which is in error. See, had you got this value as all zeros, had C4, C3, C2, C1 been equal to this, it would have indicated that there is no error in the transmission. But what did you get? You got a non-zero value. What did you get? You got this. You got 0011 in binary. Now if you convert this to decimal, you get 3, which means that bit position 3 is in error. So which is bit position 3? 1, 2, 3. Yes, it is the bit which we purposely changed in order to verify whether Hamming code works or not. Yes, this has been changed. That means I have correctly identified the position of error. So what is the position of error? The position of error is the third position. What does it contain? 1. How do I correct it? Simple. I'll simply take this 1 and I'll convert it to 0. In that way, Hamming code is not only able to detect the position of error. See, how did it detect the position of error? It found the value of 3 for this error code. It found the value of 3. That means it correctly detected that position 3 is in error, And how did it convert, or how did it correct the error? It corrected the error by flipping the bit, by simply complementing the bit from 1 to 0. Since you're dealing with bits, and since you'll always deal with single bit errors for Hamming code, all you need to do to correct an error is to simply change either a 0 from 1 or from a 1 to 0. So in this way, Hamming code is able to detect as well as correct errors. So this was a long video. I hope you have understood all the numericals. If you have any doubts, please feel free to comment in the section below. I'll see you in the next one. Thank you.